Alright, now that we know how to calculate friction, we need to apply this to free body diagrams, because this gives you a different way to find all the pieces to the puzzle. Okay. So as a quick review, we're going to still stick to Newton's first law for right now. So remember, Newton's first law is represented if your object is at rest, if your object is moving at a constant speed, and both of these mean, so they both mean that your net force is going to be equal to 0. Alright? Which, another way of saying net force is equal to 0, all forces cancel out. Okay? So, before we move into some free body diagram problems, there's two things you need to know. There are actually two types of coefficients for every single surface. Alright, so like the table that you were working at, or the piece of carpet, or whatever. They each have two coefficients of friction. The first coefficient of friction is the coefficient of static friction. And especially if you were the person watching and taking the measurements on the Newton meters, you might have noticed that initially, in order to get the block moving, the force jumped up. And that is because it takes more force to get the object moving. The coefficient of static friction is higher than the coefficient of kinetic friction, which involves actual movement. Okay, so static friction is at rest. So static friction, you use that coefficient when you're at rest. This is always, 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 always higher. Alright, it takes more force to get the object moving than it does to just keep it moving. Alright, and then we have the coefficient of kinetic friction. Alright, and this is when we have an object moving at a constant speed. Or also when we get back into Newton's second law and working with acceleration. That would also be the coefficient of kinetic friction. Okay, and that's just because once you get the object moving, it's easier to keep it moving. You've probably even noticed this if you've tried to push something that's really heavy. It's hard to get it going, but once you have it moving, it gets a little easier. Alright, I'm going to color code this just so you know. We already know that mu, the funky m, stands for coefficient of friction. The mu of static friction gets a subscript of s. And then mu for kinetic friction gets I bet you're guessing, a subscript of k. So that's how you can tell the difference. That way you don't have to sit there and write out coefficient of kinetic friction every time. You can just write mu k. Okay? So if you see that on a quiz or a test, know what that means. So, two questions that I want you to try. Which coefficient would you use if the object is at rest? And then which coefficient would you use if the object is moving at a constant speed? Hopefully you are saying mu s, coefficient of static friction, static, for the first one, and mu k, or kinetic, for the second one. Alright, so let's apply this to some problems, get some practice. You'll note that in this problem, for a table, you have both coefficients. Alright, so I expect you to choose the right one. So remember, the S stands for static, that's when it's at rest. The K stands for kinetic, that's when it's moving. So we have two coefficients. We have a mass. And then it says, what is the maximum force you can apply? That should hopefully imply something to you. To the book without moving it. So if it's without moving, what does that mean about the object? It is, hopefully you're saying, at rest. So based on the picture that we have here, let's draw a free body diagram. You'll have to draw these on the quiz this week. It's the best way to not lose the information. So let's draw all of the forces. So automatically, should go straight to force of gravity. Always going to be there. Okay? There's also the fact is that the question is asking what is the maximum force you can apply, i.e. there is an applied force. But because we're at rest, we know this is Newton's first law. So that means both of these forces need to have something that cancel them out. So we have a normal force and we have a frictional force. So let's find out which ones we can figure out. So I'm going to write out what I know. So since it's at rest, that means mu s is our important mu. So mu s is equal to 0.54. Right? And then mu k we don't need because it's not moving. Our mass is 5 kilograms. Right? And it appears that that's all we know. Except if you're given a mass, you should automatically be thinking, oh, I can find out force of gravity. Force of gravity is equal to mass times gravity, which is going to be the 5 kg times 10 meters per second squared, which will end up being 50 newtons. So this is 50 newtons. But that also means that since this is a first law free body diagram, normal force is also 50 newtons. So that gives us another known. F of n is equal to 50 newtons. So that takes us to another equation so that we can find the force of friction. F of F is equal to mu times F of n. We know mu, we know F of n. So that's going to be 0.54 times 50, which is equal to 27 newtons. So now we know F of F is equal to 27 newtons, which, because it's a first law problem, means that for the applied force also has to be 27 newtons. As long as you don't apply anything more than 27 newtons, you will not get that book to start moving. So that is how you do these sorts of problems. As we continue on with forces, the problems become multi-step. You absolutely must get a handle on keeping track of your information. So let's do one more. So for this one we have a table, again, same table, same book, except this time we are moving the book at 2 meters per second across the table. Now, our units here, meters per second. That makes this a what? Hopefully you're saying a speed or a velocity. And do those help us at all with finding out forces? Hopefully, again, you are saying no. All this does is let us know we're dealing with first law. Alright? So we have a book moving at a constant speed. So again, draw a picture. We have force of gravity going down. We have normal force going up. If it's moving at a constant speed, there has to be some sort of applied force getting that going, and a frictional force keeping it at a constant speed. Alright. So now let's go through the information that we have. It's similar to last time, except now we are moving the book, so that means that mu k is the coefficient of friction we want to deal with. Then mass is still 5 kilograms. And it starts out the same way as last time. We need to start finding some of our forces. Easiest one to find is force of gravity. So that's going to be 5 kg times 10 meters per second squared, which ends up being 50 newtons. Alright, and then because force of gravity is 50 newtons, and this is a first law problem, normal force has to be 50 newtons. Okay. So now we know F sub n equals 50 newtons, which takes us to another equation we have enough information for. Force of friction is equal to mu times F sub n. So that's going to be 0.42 times 50 newtons, which is equal to 21 newtons. And once you know force of friction, with this Newton's first law problem, you know force applied. Okay? These are not hard unless you are incredibly disorganized with how you do things. Alright? So, I would say get into the habit of drawing the diagram, drawing all the forces that are supposed to be there, then figure out what forces if the problem gives you a force, write that force on the diagram. If it doesn't give you a force, but you have a mass, you should go automatically to force of gravity. Okay? And then once you have force of gravity, if it's Newton's first law, or if you're sitting on a table or whatever, now you have normal force. Now that you have normal force, that might help you find force of friction. Alright? These are not that difficult as long as you stay organized. So make sure you do the online form, and I will see you in class.